Gentlemen, it's Thompson here again. Wayne, AJ, let's get moving. We're looking at Earth's magnetic field. So Earth has a magnetic field that's very similar to a bar magnet. We have, of course, something known as it's obvious here. The geographic North Pole and the geographic South Pole are not quite in line with the magnetic poles of Earth. Okay. Notice that near the geographic North Pole, we have the South Pole of the Earth. And of course, near the geographic South Pole is the North Pole, North Magnetic Pole of Earth. Okay? So Earth's magnetic field is strong and perpendicular at the poles, which means perpendicular to the surface. Towards the geographic north, it points straight down. Towards the geographic south, it points straight up. Okay? And so it says Earth's magnetic field is weaker and parallel at the equator. And so the geographic south is pretty close to the magnetic north and vice versa. So geographic north is similar to the magnetic south. That's what makes navigation possible here, because when I use a compass on the surface of the Earth, it points towards the geographic north. And because the north pole of a compass points towards that, it must be a south magnetic pole in the geographic north, okay? And vice versa. Let's take a look at domain theory. So iron, nickel, cobalt, and gadolinium are the only elements that can be affected by a magnetic field. They're called ferromagnetic materials. Ferromagnetic materials are composed of domains, which are tiny magnets created by electrons that spin in the same direction. And so we look at two types of materials here. One's unmagnetized ferromagnetic material. And so these domains are randomly oriented. The magnetic fields cancel each other out, and we call it unmagnetized. A magnetized ferromagnetic material. Now, if we bring in a magnet nearby a ferromagnetic material, we make it magnetized. We hadn't paid our power bill. I'm sorry about that. Like I was saying, you bring in a magnet very close to a piece of ferromagnetic material, and these domains line up. They all orient themselves in a given direction. Okay? And so the external magnetic field aligns the domain. That makes the material called magnetized. And the magnet induces the opposite pole in the closest region. It says, note, right, soft ferromagnetic material like iron gains and loses magnetism quickly. It's good for temporary magnets used inside electromagnetic devices. Hard ferromagnetic material, right, to contrast, like an alloy, keeps magnetism for a long time. It's good if you wish to make a permanent magnet. Okay, let's look at some practice kind of questions here. So it says determine the direction of each number compass, North Pole in the diagrams below. Notice we talked about a magnetic field that should loop around from the North Pole, exiting and coming into the South Pole. So that means at 1, it should be pointing in this direction. Okay? In 2, it should be pointing in that direction. Notice the letter we use. We use B for magnetic field. Between two south poles, the field line should be going in. Like this. And so when I look at each one, what do you think the direction should be here? Well, for compass 1, it should be going that direction. And for compass 2, it should be going that direction. Okay? Using a vector sum diagram, determine the direction of the net magnetic field at P. So for this first one, the North Pole has a magnetic field that goes outwards, and so the first vector should point this direction from here. From the south, it should be going this direction. And so, tail to tip method, we're looking at the net field, which would be here. Okay? That net field. All right, take a look at this one, Ray. So what do we have? We have a vector that goes outwards here. This one goes that direction, and this one goes this direction. So summing those three vectors together from point P, kind of like this, we would have one vector down, in order I do them, one that goes over, and then another one that goes over. And so the net field this direction. Okay. Take a look at question 3. Explain the following using domain theory. We can just do this orally. And it says here, why does the south pole of a magnet get attracted to a metal fridge door? Well, the fridge door must have some ferromagnetic material in it. And what's really happening using domain theory? Well, if you take a look, the south pole, right, is brought in close, which is going to induce a magnetic field, a north pole on the ferromagnetic material. So the domains line up to point towards that south pole that approached. And the north pole of the ferromagnetic material and the south pole of the magnet attract each other, so the magnet sticks to the fridge. It's a good thing. You can post some of your work for your parents to see on the fridge. Good idea. Heating or dropping a magnet can cause it to lose its magnetism. Well, heating it or dropping it, that really tries to make the orientation of the domains more random. It tries to distort them a little bit. It's adding energy. Okay? And so they might just return to their random directions, kind of like shaking them up. How can you use a strong magnet to reverse the poles on a bar magnet? What you need to do is you need to use the strong magnet to be able to adjust the magnet, generally by contact. So what you do is you take like the south pole of it and move it along, right, the magnet. And what happens is, if you take the south pole and move it along, then of course you're trying to reorient the domains. The south pole, of course, most people use the north pole to do it, but you can use the south pole as well. What you do is you just stroke it along there, and it will eventually, right, starting with the south pole and then moving towards the north, it'll adjust and randomly orient the domains. Then eventually it'll start to strengthen them in the other direction. And then the last part here, building beams are found to be magnetized due to the combined effects of the Earth's magnetic field and vibrations created during construction. Okay? Well, the metal beams must be hard ferromagnetic materials. So during construction, the domains are shaken up, and since they're now easier to move around, they'll align in the same direction as the Earth's magnetic field. This magnetizes the beam. Okay, so the idea of creating a magnet. We've probably done this before. All right, gentlemen, take a read over it, see if you get it. Let me know if you have any questions. Thank you.